Thus far, all of our solutions to our series have been about ordinary points. In other words, they're within the domain and they're analytic at a specific point. Let me show you what happens if we use the method that we've been using for some sort of singular point. And remember, we talked about these idea of singular points to where a function's not analytic, meaning its power series doesn't exist at that point. So take a look at this differential, a really basic one. Let's say we have the differential xy prime plus y is equal to 0, and we want to try to find the solution about this time singular point x sub naught equals 0. And why does x naught equal 0? Is that singular? Well, if we substitute it in, that just means that the y prime just goes away and we're left with y equals 0. That doesn't mean that there's not a functional solution that makes this correct. All right, so let's just use the old method that we've seen so far. So we're going to let y be equal to series n equals 0 to infinity, c sub n x minus 0 to the n, which is really just x to the n. All right, so I'll just get rid of that so that way we don't have to rewrite it. And by now we know what y prime is. Y prime is going to be equal to series n equals 1 to infinity, c sub n n x to the n minus 1. And let's substitute those back into the original differential. And so our original differential becomes x series n equals 1 to infinity, c sub n n x to the n minus 1, plus n equals 0 to infinity, c sub n x to the n equals 0. Now, we can do two things. We can multiply the x inside, and then also we can split off n equals 0 to this series. And that should put it to where we can factor out the series as well as the x to the n. So I'm going to break off and I'm going to multiply the x into this, and we're going to get series n equals 1 to infinity, c sub n n x to the n now. This is c sub n, and then x to the n, since this is x to the first, and that's going to cancel those out, plus series n equals 1 to infinity, c sub n x to the n, and then I'm just going to substitute 0 back in, right, to break off that n equals 0, and that's going to be c naught x to the 0 equals 0. Or in other words, c naught x to the 0 is just c naught, since x to the 0 is 1. Now we can factor the series, and we can factor the x to the n, and so when we factor that out, n equals 1 to infinity, x to the n, and we will be left with cn times n plus cn plus c naught equals 0. All right, so far everything's good up to this point. And now we know already that the series, the only way that that's going to add up to 0 for x to the n is if x is going to be equal to 0, which is the trivial point anyway. That doesn't matter. Another equation that we can get is usually going to be the generating function, c sub n plus cn equals 0. And then finally, we know at this point, the only way to add a constant, if this whole thing has to be equal to 0, that means that this whole series has to be 0, and also this has to be 0. And so that means that c naught is going to be equal to 0. All right, so let's just hold on to that. We're going to factor out the cn, and that's going to leave us with n plus 1, which is equal to 0. And the only way that that's going to be true is if n is equal to negative 1. But that can't be true because notice that n is equal to 1, 2, 3, 4, 5, etc. n is never negative 1. So the only way for this to be true is when c sub n is equal to 0. And what that means is that our series, we don't have to go through and do anything. We don't have to go through the method of iteration, because even if we were to divide by n plus 1, we would get c sub n equals 0 anyway if we divided this expression by n plus 1. All right? And so what that means is that y is going to be equal to the series n equals 0 to infinity. Remember, c sub n is 0, so that's going to be 0 x to the n, or in other words, y equals 0. But we know there's got to be a function that we can substitute. All right, so how about this trick? And this is one that we haven't seen before. And this has nothing to do with series, but let's let y be equal to x to the r power, where r is just some real number. Okay, that means that y prime is going to be equal to r x to the r minus 1. And let's plug that back into the differential. Remember, we have xy prime plus y is equal to 0, and that's going to become x times r x to the r minus 1 plus x to the r, which is equal to 0. We can simplify the first term. X times r minus 1, or x times x to the r minus 1, x and the negative 1 go away, so we get r x to the r plus x to the r is equal to 0. Or in other words, if we factor x to the r out, that means we get r plus 1 equals 0. Now, we can't necessarily get a solution to this. Okay, this will never equal 0. All right, unless for some reason we plug in r is negative infinity, which really doesn't make any sense. However, this is pretty easy, that we get r equals negative 1. And we can just substitute that now back into the original differential, and we can get a solution, y equals x to the minus 1 power. Right. Does that work? Well, we know that y prime is negative x to the minus 2. And if we substitute back into xy prime plus y equals 0, that gives us x times negative x to the minus 2 plus x to the minus 1 equals 0. Does that work? Well, that gives us opposite x to the minus 1 plus x to the minus 1 equals 0. Clearly that does work, so this is a solution. However, x naught equals 0 is not in the domain of y equals x to the minus 1. All right, so what does that mean? I mean, this is clearly a solution. All right, so y equals x to the minus 1 is clearly a solution, but it's not a solution at x sub naught equals 0. So how do we get around all that? Well, what we do is we come up with this new method. And the method that we're going to come up with is something called the method of Frobenius. Okay? The method of Frobenius couples these two ideas to where we use this x to the r and that trick to be able to find a series solution. All right, so if x sub naught is and we're going to define regular singular, is a regular singular point, then we use the following series instead. That's going to be y equals x to the r series, n equals 0 to infinity, c sub n x to the n. All right, so we use the two methods that we had. All right, so we just showed that that trick that x to the r will work, and r is not a positive integer. All right, notice right here that r at that n equals 0, 1, 2, 3, 4, 5. They're almost all positive integers. This is not a positive integer. So it's really cool that this trick can be able to help us to find a non-positive integer. All right? Another way to write this, and excuse me, that is only valid if the singular point is 0. So a more general solution for this would be x sub x naught to the n. Okay, or another way that we can write this, and this would have to be over here, x minus x naught to the r power. And so we can kind of multiply that inside. Right? So this becomes x minus x naught to the r, y equals that, and we could just kind of multiply this inside here, and so that gives us the method of Frobenius, where y is going to be equal to series n equals 0 to infinity, c sub n, x minus x sub naught to the n plus r. Right? So in reality, we're only going to be adding in this factor, this sum here, okay, n plus r instead of n, and that's our method of Frobenius, okay? Now, r is a real number, all right? So, and it is possible for r to equal 0, and if r equals 0, that means that originally the series was probably analytic at that regular singular point. All right, so what does the method of Frobenius mean? Well, first of all, we have to identify what a singular point is, and then furthermore, we have to identify a regular singular and an irregular singular. Now, regular singular basically means that if we have a differential of this form, that means a singular point is such that when we substitute it in, this just makes the second derivative, or even the first derivative like we saw, go to equal to 0. Right? If we were to divide everything by that a sub 2 of x, then what that means is that x minus x naught appears at most of the first power in the denominator of p, and p is going to be the coefficient of y prime, and it appears at most in the second power in the denominator of q. All right? And so if it's not a regular singular point, then it's irregular. And that means that we probably have to use a numerical method to be able to find the solution. And so before we conclude this video, I just want to illustrate how we can determine if a point is, how to determine the singular points and then classify them as regular or irregular. All right, so for this very first example, a nice easy one, we have x cubed y double prime plus 4x squared is equal, or plus 3y is equal to 0. Now, I think everybody can see that x sub naught equals 0 is singular. All right, and the reason it's singular is if we plug it back into x cubed, that's going to make y double prime go away. All right, so that's pretty obvious. And so the question is, well, is it going to be regular or irregular? So let's divide everything by x cubed. And if we divide everything by x cubed, we can rewrite this as y double prime plus 4 over x y prime plus 3 over x cubed y equals 0. All right? And at this point, what we can suggest is that this is not going to be regular. And for this one, it's okay. The power is 1, so x to the first, that's okay. But right here we have x cubed, and that's not okay. Right? So it appears 3 times. So we're going to say that that is an irregular singular point. And that means we cannot use Frobenius. Right? A second example. What we're going to do is we're going to say we have x squared y double prime, and then plus x plus 3y prime plus 2y equals 0. And I think everybody can see that x squared minus 9 equals 0 is going to yield the singular points, or x would be equal to plus or minus 3. We could divide everything by x squared minus 9, so we would get y double prime plus x plus 3 over x squared minus 9 plus 2 over x squared minus 9 y, and I forgot the y prime there, is equal to 0. And even if we were to factor this and simplify it, it really doesn't matter, because x equals plus minus 3 appears once each in the denominator, and then it also appears one time in this denominator. And so because it only appears at most one time, and just to show you, I could factor this down just to illustrate this point. All right, and I will. So if I was to factor this, I would get y double prime plus x plus 3. We could factor x squared minus 9 as x plus 3, x minus 3. Clearly those would go away and just leave us with 1 over x plus 3 y prime plus 2 over x plus 3 x minus 3 y is equal to 0. And notice that we have an x minus 3 of multiplicity 1, x plus 3 of multiplicity 1, x minus 3 of multiplicity 1. So if the multiplicity, or the number of times that the factor appears in the denominator, is just once, then it really doesn't matter. All right, so indeed this is going to be a regular and singular point. Okay, so x equals 3, and x equals -3 are both regular and singular. Right? And what that means is that we can use the method of Frobenius on both of those. A final example, we have x squared plus 1, y double prime plus y, all right, x squared minus 1 squared. And so let's go ahead and divide, and clearly we know that x naught is going to be equal to 0 is one singular point, and then also x squared plus 1 equals 0, or actually x squared plus 1 squared equals 0, all right, just to be completely transparent about this. And then x squared plus 1 equals 0, and that means that x squared is -1, which means that x equals plus minus I. All right, so these are the three singular points. Now, we're going to divide everything, so we're going to get y double prime plus 1 over x squared plus 1 squared, y equals 0. Now notice that x equals 0 appears once. It has a multiplicity of 1. X squared plus 1 squared means that x equals plus minus I appears twice. But that's okay, because it's in the denominator of q. All right, so remember, if we go all the way back up here, remember, it can appear twice in the denominator of q, and q is the term or the coefficient in front of just y. All right, so what we can say is that x equals 0 and plus minus I, or even x naught equals 0 plus minus I, are regular singular points. All right, so hopefully this gives you a good idea as to, first of all, how to identify singular points, how to classify them as regular or irregular, and then also the whole method of Frobenius as to why we need this. So in the next video, what we're going to do is we're going to outline the process, and we're going to go through a really basic example of the method of Frobenius.